Hello and welcome to this lesson. In this lesson, we utilize the design methodology described in the previous lesson. Now, we illustrate it with a case study which is microprocessor based temperature monitoring and flow control system. Do you think that it is necessary to understand the user requirements first prior to going into the design? Of course, yes. Before we take up the system design, we should know in detail about the temperature range of the process, accuracy desired in measurement of the temperature, nature of the chemical, whether corrosive, fuming or neutral, and the time interval between two consecutive operations being performed in the industry ideally. On interaction with the end user, we analyze his requirements and define the technical specifications of the system accordingly. The process temperature range for the system is 20 degrees Celsius to 80 degrees Celsius, whereas the temperature measuring accuracy for the system is plus minus 1 degree Celsius. The accuracy in pouring the chemical in the process is plus minus 5 ml. The three steps defining the amount of chemical to be added in the process with respect to temperature are: 200 ml chemical is to be added in the process up to a temperature of 40 degrees Celsius, whereas 400 ml for temperature between 40 degrees Celsius to 60 degrees Celsius. For temperature above 60 degrees Celsius, we add 600 ml of chemical in the process. The provisions for visual display of process temperature and audio-visual indicators are provided for the operator regarding status of the system. Keeping into the consideration the technical specifications of the system, we now define various hardware blocks which have the capabilities to achieve the defined technical specifications. We use popular 8-bit microprocessor Intel 8085 and interface various devices with it using its address, data and control buses. Two memory devices, EEPROM and SRAM, are interfaced with the processor for storing program and read, write, arithmetic and logical operations. To enable the user to command the system in accordance with his requirements, we provide a provision for operator's panel and a display unit which are interfaced with the processor. For measurement of temperature and flow control of the chemical, we interface the temperature transducer and a control circuit with the processor for accomplishing these tasks. For software development, the temperature monitoring and control flow can be divided into 3 steps, namely: the system waits for operator's command. On receiving the appropriate command, it measures the temperature of the process, displays the temperature and finally adds the defined quantity of chemical with respect to temperature. On completion of these tasks, the system is again ready to receive and process the next command, if any, generated by the operator. Considering the technical specifications, reliability, repeatability, and economic factors, we now take up the circuit design of the system in accordance with the block diagram. We select various devices and components to convert these defined blocks into reality. We know that microprocessor 8085 can source 400 microamperes and sink 2 milliamperes of current. This current rating suffices only for one transistor logic load. Therefore, we select an octal buffer 74LS244 for the higher order address bus A8 to A15 and an octal latch 74LS373 for the lower order address bus A0 to A7 to increase the drive capacity of the processor address bus. We can also use 8212 chip in place of 74LS373, but it is costly and not available easily. However, we use an octal transceiver 74LS245 on the data bus as it is bidirectional. On the control bus, we use an octal buffer 74LS244, which enables the processor to drive more than one devices connected with it. To realize the memory section of the block diagram, we interface 2716 EEPROM and 6116 SRAM with the processor. These chips have the capabilities to store 2 kilobytes of data and program into the SRAM and EEPROM respectively. These memories are interfaced with the processor through address, data and control buses. The memory map for EEPROM is 0000 to 07FF. Since the program counter of processor is cleared to address 0000 whenever the system is reset. However, memory addresses for SRAM are 0800 to 0FFF. For operator's interface and display unit, we use 8279 keyboard and display controller chip. The 8279 chip has capabilities to control the 16 keys keyboard through scan and return lines. The 8279 chip also controls the 7-segment FNDs which constitute the display unit. The 8279 is interfaced to the processor through its address, data and control buses. For temperature measurement, we use chromal alumyl thermocouple having a sensitivity of 0.004 millivolts per degree Celsius. Do you think that the voltage level of the sensor output is sufficient for analog to digital conversion? No, not at all. Therefore, we use a two-stage amplifier circuit to amplify the sensor output. The amplifier circuit constitutes OP07 operational amplifiers. The first operational amplifier provides a gain of 100, while the second operational amplifier provides a gain of 70. Therefore, the total gain provided to the sensor output is 7000. The amplified sensor output is now compatible with the voltage level required by analog to digital converters. The analog to digital converter ADC 0801 is used to convert the analog data corresponding to the process temperature to its digital equivalent. The ADC 0801 is interfaced with the processor through programmable peripheral interface 8255. The 8255 chip provides us three 8-bit ports, port A, port B and port C respectively. The PC0 and PC4 lines of port C are used as output and input port respectively to control the analog and digital conversion operation. The PC0 line initiates the conversion, while PC4 line is used to analyze whether the conversion is over or it is under process. The port A of 8255 is used in input mode, and we connect it with data lines of ADC chip 0801. The processor reads the port A to acquire digital data generated by ADC 0801 corresponding to amplified sensor output. The port B of 8255 is being used in output mode for generating the audio and visual indications regarding status of the system. However, the PB7 line is dedicated to fire the control circuit for pouring chemical into the process. The 8255 programmable peripheral interface chip is interfaced to the processor through its address, data and control buses. In this manner, we integrate the analog to digital converter ADC 0801 audio and visual indicators with the processor. The PB7 line of 8255 port B is connected to drive an optocoupler which provides isolation between digital and control circuit. The optocoupler activates a 400 volts 4 amperes triac, which in turn activates the solenoid valve. As solenoid valve goes to on state, the chemical starts pouring into the process. By controlling the on time of solenoid valve, we add appropriate amount of chemical into the process. On completion of circuit design, our next step would be to convert the desired operations of the system into detailed flowcharts. We follow a modular approach, and for this purpose we divide the complete system functions into 3 steps. Step 1, initialization of the system hardware. Step 2, to sense temperature of the process, and step 3, to activate the control circuit. Now we define these 3 steps in terms of detailed flowcharts, enabling us to write efficient programs which drive the system hardware. In the first step, we initialize the keyboard and display controller chip 8279 and generate a sign-on message ready. This indicates that the system is waiting for operator's command. The moment processor receives appropriate command, it goes to step 2, that is to measure the temperature. Otherwise, the system waits for appropriate command. In this manner, the program takes care of any errors at the operator level. In the second step, the processor measures the process temperature through analog to digital converter. To activate the analog to digital converter ADC 0801, we initialize the programmable peripheral interface chip 8255. Port A of 8255 is programmed in input mode, port C lower in output mode and port C upper in input mode respectively. Analog to digital conversion process is activated by sending initially a logic 0 and then a logic 1 at port C lower. The processor analyzes the end of analog to digital conversion process through port C upper. If the conversion is not over, the processor waits for it. On completion of the analog to digital conversion, the processor inputs the data through port A, calculates the corresponding temperature in degrees Celsius and finally displays it. In the third step, we activate the control circuit to add a predefined amount of chemical into the process with respect to the process temperature. For this purpose, we calculate the on time for solenoid valve in correspondence with the process temperature. We initialize port B of 8255 in output mode and output a logic 1 signal on PB7 line. Now we provide a delay equal to on time already calculated. We maintain logic 1 at the PB7 line of 8255 till the delay is equal to on time to keep the valve in on state. On completion of delay, we output a logic 0 at PB7 line to switch off the valve. The processor now goes back to step 1 and waits for another command from operator, if any. This completes the software design for the system to achieve the full functionality of the system. Now we integrate the system hardware and software and test it in accordance with its technical specifications. We debug the system for its failures, if any. To do so, we define 3 stages for the debug and test procedures. In the first step, we test the system up to PPI chip 8255 in input and output mode. If there are any malfunctions, we analyze signals, read bar, write bar, chip select, address, data and control buses and rectify the faults. In the second step, we integrate and test the analog to digital converter ADC 0801 with the transducer. The temperature transducer is calibrated in the specified temperature range. We also analyze the accuracy, resolution and repeatability of the transducer critically. Now we execute software developed till second step and analyze the results. In case of malfunctions, we analyze the status of write bar and interrupt bar signals on ADC 0801 chip. and the mode of ADC operation. In the last step, we test the control circuit of the system and analyze its functioning. We execute software developed in third step and observe that the solenoid valve should be on for the defined time. If it is not, we analyze signal levels at the optocoupler, gate input off track, solenoid valve and take the corrective actions. In this manner, we can define the debug and test procedures in a way which adopts a portion of the software modules developed. Finally, we integrate the entire hardware and software of the system and analyze the system functioning vis-a-vis its technical specifications. We now install the design system at the user site and analyze its behavior in the industrial environment regarding interference from nearby instruments, power supply transients, the proper place for operator and display units. These characteristics are helpful in incorporating ruggedness and ergonomics in the design as the final touch. Now, we subject the system to burn-in tests for 48 hours. After this period, the system is checked and debugged again if it is not functioning properly. On completion of burn-in tests, we place the system in a heat chamber for 5 to 6 hours. Finally, we subject the system to vibrational and humidity tests. We do it to ensure that the semiconductors do not fail for any reason after a few hours of operation. After performing these burn-in tests on the system, we fine-tune all the adjustments to achieve the best performance in accordance with technical specifications of the system. In this lesson, we have undergone the design process of a case study entitled Microprocessor Based Temperature Monitoring and Flow Control System. The design process of the system brought together all the concepts of requirement analysis, system specifications, microprocessor architecture, hardware and software design, interfacing analog to digital converter and control circuit with the microprocessor 8085. And the case study included debug and test procedures besides the burn-in tests for proper operation of the system as per user requirements.